This is the 2008 BC Form A FRQ number 3 on Taylor series. And let's read this to make sure we're not missing important things. Let H be a function having derivatives of all orders for x greater than 0. So the derivative exists for all of these. Okay. Selected values of h and its first four derivatives are indicated in the table. The function h and these four derivatives are increasing. Okay. H and the four derivatives are increasing. There's probably a reason they told us that, so let's pay attention to that. So part A, write a first degree Taylor polynomial. First degree. That is actually pretty easy. So we're going to build a Taylor polynomial with degree 1. So starting from scratch, and it's about 2, it's going to be the function at 2 plus the derivative at 2 times x minus 2. That would be it. You don't have to write that line down. I do that to show you where it comes from. H of 2 would be 80, and h prime of 2 is 128. So there is our second degree Taylor polynomial. And to approximate, h at 1.9 is approximately equal to what? All we do is plug in 1.9 and we're done. Oh, whoa, I don't know what just happened. 1.9 for x. Now we're done. That is our approximation. You don't have to simplify that. You should leave it. For those of you who are foolish and simplify it, you should get 67.2. And that's our Taylor polynomial. So we could say that's P1 at 1.9. Here, let me rearrange this because that's improper. This is P1 at 1.9, and that's going to equal that, but this is approximating h at 1.9. That makes sense. Then it asks us, is this approximation greater than or less than h at 1.9? How do we figure this out? Well, remember, a first degree Taylor polynomial is actually a tangent line approximation. It is a tangent line approximation. So because it's a tangent line approximation, remember, concave up, tangent line is below, concave down, tangent line is above. Now if we look at the second derivative, it's positive. Now, couple of things to note for second derivative. It's positive, and the second derivative is increasing because all derivatives are increasing, so it's never negative. The second derivative is always positive from 1 to 2. Therefore, it's going to be an under approximation, okay? So I'm going to write this down. H double prime is greater than 0 from or on the interval from 1 to 3. Okay, again, how do I know that? Here's h double prime, starts at 42, goes up to that, and it's increasing. So if it starts at 42 and is increasing, we know it's positive. Therefore, P1 of 1.9 is, okay, h double prime is positive, so it's under. It's going to be under. Okay. Is less than. I'll just here. Why am I doing this? Just put the less than signal. Less than h of 1.9. There we go. So that's the answer to part A. And there's other ways to get this. You could also say since, and this is what the solution said, since h is increasing, therefore h double prime is positive. Because if any function is increasing, its derivative is positive. So you can use that logic also. But just looking, it starts at 42, is increasing So it's going to be positive in our region. So we're good. Part B, write the third degree Taylor polynomial and use it to approximate h of 1.9. Okay, we're going to do the same thing, but now we're just going to add a couple more terms. So it's going to be h of 2, h prime at 2, x minus 2, h double prime of 2, x minus 2 squared. Oh, yeah, over 2 factorial. And then h triple prime of 2, x minus 2 cubed over 3 factorial. And now we just replace the values from the table. And what do we get? 80. And the next one's 128. We already had that from before. And then h double prime, that's kind of a weird one. It's 488 over 3. But the 2 is also down there, so I put that there. And you can multiply that out and get a 6 on the bottom. I'm just going to leave it like that. And then h triple prime, it's going to be 448 over 3. I don't know how that happened. 448 over 3. You also have a 3 factorial. Now you could 6 times 3 and get 18 there. And 18, you can divide top and bottom by 2. You could do that, but not necessary. We're good. And then it says use it to approximate h at 1.9. So h at 1.9 is about P3 at 1.9. And then we replace all of the x's with 1.9. And do not simplify. You do not need to. That would be like dumb if you did that. And you did a dumb error. 1.9 minus 2. I'm running out of room on this screen. 3 times 3 factorial. That is your answer. We are done. If you were to be foolish and simplify that, apparently that's 67.988. But, you know, I just realized this year's a calculator questions. You're allowed to use a calculator, but even though you're allowed to use a calculator, I would not simplify that. What if you punch a wrong number in anywhere? That would be no bueno. All right, so we're going to do part C. Use Lagrange error bound to show that the third degree Taylor polynomial for h about x equals 2 approximates h at 1.9 with the error less than 3 times 10 to the 4th. So Lagrange says the error is less than or equal to the maximum of the next unused term. So this is a third degree. We want the 4th term, which we didn't find, but we can do this. We know how to find it. It's going to be the max, and our values of C are going to be between the center, which was 2, and the point being estimated. We're estimating 1.9. It's centered about 2, so our C's will be between 1.9 and 2. And we want the next term, so we use it's a third degree, I guess, third. So it's going to be the 4th degree term, which is the 4th derivative at some point C. And I'm kind of messing up here. So the maximum of the 4th derivative at some point C times x minus 2, but it's going to be 1.9 minus 2. I do need absolute value here because that's going to be negative if I don't. To the 4th power. Well, actually, the 4th power would make it positive anyway, so in the end, it doesn't matter. Over 4 factorial. Now, all I do is plug in values. This is less than. Now, here's a question. What is a number for the 4th derivative between 1.9 and 2? The 4th derivative between 1.9 and 2. Well, here's where the fact that it's increasing is going to be largest at 2 because we learned that the derivatives are increasing. All 4 derivatives are increasing. So if you're going from 1.9, which is down here, up to 2, the maximum will be at 2. So that is going to be replaced with 584 over 9. 1.9 minus 2 is negative 0.1, but absolute value is going to be 0.1 to the fourth, all over 4 factorial. And we want that less than 3 times 10 to the negative 4. So that's it. We're done. If you want to simplify that, I guess you could, but we should be fine without simplifying that. No, we should be, we are, as long as we plugged in the right numbers, which we did. So that's it.